The iNGENIOUS transport use case focuses on rail health condition monitoring. The transport use case is led by Neurocontrols and supported by Barkhausen Institute. The focus of the transport use case is to demonstrate next-generation micro-edge computing with remote attestation on self-powered mobile applications. Like an AirTag, such sensors should be performant, have a very long lifetime to support industrial applications, and be safe and secure with respect to communication and cybersecurity. Long lifetime means fault-free operation without maintenance and without recharging requirements. Safe and secure means utmost robustness against cyber attacks and information loss. Our solutions are demonstrated in one of the most difficult use cases, namely rail health, but could be applied jointly or independently to any other domain such as health, industrial, finance, IT, and other. In rail health, we demonstrate that with technological innovation, hitherto impossible commercial rail application requirements can be achieved, which opens up new markets, improves rail safety, and reduces avoidable rail infrastructure damage. The transport use case focuses on condition monitoring of rail bogies to prevent carriage derailment and rail infrastructure damage. Flat spots and bearing defects in various combinations and intensity must be detected reliably. Commercial rail focuses on minimizing asset downtime and dealing with critical problems just in time. Non-critical issues must be differentiated from critical issues. Problems must be staged into various severity classes, and the solutions must be cost-effective and easy to retrofit. They also must meet ARTEX explosion requirements, functional safety compliance, and exhibit safe and secure communication capabilities. Problems must be identified as they occur to determine time and location for traceability, and data transmission costs shall be as low as possible. The operational lifetime on battery operation shall exceed 12 years. All these requirements make rail health a very challenging use case. The state of the art before we started this project was passenger rail health monitoring. This meant 2,000 euros of sensors per rail carriage, factory pre-installment and fixed wiring for power and communication buses. We have moved the benchmark to low-cost, low-powered IoT sensors with state-of-the-science cybersecurity communication and are on track to achieve the ambitious cost targets while meeting the significant increases in performance requirements. We believe we managed to move the technology benchmark on remote attestation and cyclic condition fault monitoring. Our mission is nothing less than to establish cyber-secure, safe communication as a next standard in secure IoT communication, and making cyclic condition fault monitoring possible in self-powered, energy-harvested vibroacoustic sensors. Both Barkhausen Institute and Neurocontrols managed to attract potential partners to pursue exactly these goals. Condition monitoring may not seem very sexy at first, but when internet bandwidth and electric power are not unlimited, and complex AI algorithms no longer become a viable solution, then the attractiveness of the problem increases significantly. Add to this the million-plus possible fault combinations and very limited datasets, and the solutions no longer become straightforward. Trying to improve on previous approaches was probably our biggest mistake. Our solutions became so complex and so expensive that we would have missed the low-cost, low-power targets. When we finally moved from complex filters and features to extremely elegant envelope algorithms, simple features, and model-based inclusion signatures, we were able to drop generic AI approaches like neural networks, neuromorphic networks, and machine learning in favor of intrinsic solutions, which could also easily be encoded on FPGA. A viable FPGA solution is essential, as it will allow to move to low-power silicon solutions in subsequent steps. The FPGA approach was also pursued by Barkhausen Institute. Moving the remote attestation solution from the lab to the field requires silicon IP, which can be easily integrated in state-of-the-art controller architectures. The IP developed for rail health condition monitoring will be a game changer in this industry, but it can also be easily transferred to other industrial applications to lead the way in cost-effective vibroacoustic micro-edge condition monitoring solutions. We have validated our algorithms with real-world data, with synthetic data, and mechanically fault-generated data. This allowed us to understand the physics, test thresholds, and truly understand the reliability and limits of our approaches. We have collected 12,630 real-world datasets, generated hundreds of simulated datasets, and recorded a large number of mechanically generated fault datasets. This made this project very material and hardware intensive, on top of the allocated research resources. The demonstration will show the achievements to date, but of course, we never stop dreaming of things to do next. During the course of the project, we have explored 8 core technology approaches which will enhance rail health monitoring in terms of economics and performance. These are energy harvesting in order to achieve 25 plus years of lifetime operation, always-on triggering in order to be able to determine the time and location of incidents, micro-edge sensing in order to achieve low power consumption, mesh networks and long-fin networks for communication power optimization, cloud validation for distributed feature algorithms, remote attestation for secure communication, and novelty loggers for systematic maturity growth. As a consequence, we can make a hitherto infeasible business case feasible. For this, we are in exchange with leading SaaS partners to bring this technology to the market. Now, without further ado, let's move to the video presentation of our demonstrator.
Welcome to Dresden. We're going to demonstrate our rail health fault simulator with remote attestation. Here you see our fault generator. What we can do here is we can generate different kinds of flat spots. Flat spots are ingrained here on a rolling stand, as you can see here. We can also change the bearings, and the bearings can be changed here with different faults, like inner fault and a bearing fault. We can adjust the weight, the load, via these screws, and of course we can adjust the speed. So let's go to 30 kph. Now we are in the fault-free situation. Here we have a sensor. The sensor is directly above the bearing. The signal is going to be sent to our computing unit, and when we start the computing unit, the signal is transmitted to our remote attestation device, which will then send results to our PC. So since we are in a fault-free state, you can see that we have no defects. Let's change to a fault state. Okay. Now we will go again from the sensor to our computing unit, back to the remote attestation, and you will then see over here the classification. Let's take a look at one more defect. Let's take a look at double faults. So here you see a double fault of different intensities and with a different amount of harmonics. This information is being sent to our remote attestation unit.
This attestation unit is an FPGA. It is connected via network to a Raspberry Pi single board computer that is simulating a cloud server. The idea is that the FPGA, which is running the M3 operating system, sends the received sensor data to the cloud server. The state of the art is that this is happening using the transport layer security protocol, which is based on certificates. There's an authentication step involved, and this is used to determine if the correct endpoint is receiving the data. But there's no guarantee about the software that is actually in control of this device. So for example, if a malicious attacker managed to compromise the software running on the device, such that, for example, it leaks the data, and the sensor sends the data to the device, even though the TLS protocol is happening, it cannot know that the data that will now be sent to the malicious cloud endpoint will actually be leaked. The improvement that we made in the project is that we integrated the remote attestation protocol with the transport layer security protocol. And when we now send the data again, an additional step will take place during the transport layer security protocol handshake. During this step, a hardware root of trust built into the cloud server will compute a digital fingerprint of the software running on the server. And in this case, this software is not recognized and the connection establishment is aborted. If we load the correct software and then perform the test again, the combined remote attestation and transport layer security protocol will again compute a fingerprint of the now correct software that is running on this computer. And this digital certificate about the software running will now be recognized by the sensor device and the data will be sent. And the sensor can be certain that the data will be used properly and not leaked. The sensor client running on the M3 operating system on the FPGA also attests itself to the server. On the client, RATLS requests an attestation report from M3's root of trust service. The cloud server checks the signature and accepts the client's attestation report if it recognizes the hash over the client-side software. In a separate test, we routed the RATLS connection through a simulated satellite link provided by ST Engineering iDirect. We captured what was happening during a complete transmission of sensor data from the FPGA client to the cloud server. On the top right, we see in real time what is happening on the client. We also captured packet traces during this test, which are shown on the bottom left and visualized on the bottom right. If we play back all these logs and traces in real time and in sync, we can see that only a small number of packets is exchanged and the latency is perfectly acceptable for the use case.
Finally, let's talk about project impact. NeuroControls is in close cooperation with several rail asset providers and SaaS service providers to integrate functional prototypes into the connected digital boiler car sensor platform. This activity will start from early 2024. NeuroControls is also starting a cooperation on integrating triboelectric energy harvesters in a scaled-down ARM-based solution with the goal of eliminating the battery altogether. If successful, this will eliminate battery maintenance and will prolong the service-free maintenance period of micro-edge sensors indefinitely. The commercial rail health application is a 10 million business case without legislation requirement and a 250 million plus business case in case safety legislation requirements are introduced. The maintenance-free condition monitoring sensor will take 3 or more years to complete. Its business potential is much higher. Precise numbers, however, are purely speculative. Barkhaus Institute is promoting the integration of remote attestation on advanced microcontroller architectures to industry. Barkhausen Institute has also initiated the next step of moving from FPGA IP to direct silicon implementation. An industrial size realization on remote attestation is feasible within 2 to 3 years. Judging the value of remote attestation is challenging, as it is a tool for preventing successful cyber attacks. But as computing power increases and quantum computing takes off, additional layers of protections are needed. Remote attestation will be one of those basic everyday building blocks which we will take for granted without knowing that we have it. So its value is invaluable. Barkhausen is a government-sponsored non-profit organization on basic research. Its research results are available open source. We would like to thank Horizon 2020 for supporting next generation IoT solutions. Thank you very much.